me to the end. Thank you for your attention. I would like also thank my contributors and co-authors for their work. Thanks again.
Thank you very much. So, the next speaker is Peter Kelly, who has worked for Trinity House for 23 years. Initially in the field, then as an electrical and electronic design engineer for the automation program. Latterly as a project manager, maintenance manager, and then engineering and project delivery manager. He is currently responsible for the engineering standards, asset management, and the definition and delivery of H2 navigation-related capital projects. Peter is, of course, a member of the EEP committee and also the GLA engineering committee. Peter will speak on the wider application of LED light sources into historic lighthouses. Peter.
Thank you, Eva. Appliance of science, yeah. Hopefully it'll work as well. For those in the audience who were not able to attend the wonderful seminar at Santander in June last year, I just wish to bring your attention to the recommendation number 8 from the seminar report. I therefore, in the first instance, would like to explore with you the reuse of traditional lighthouse optic prior to looking to other solutions. Looking back many years when the grand old optics were being developed, the optical engineers that back then didn't need to consider the application of small light sources as nothing existed that would be very effective. This meant that the reflecting and refracting portions of the lens were all placed to focus all of the available light from the large light sources. Over the years, developments in light sources have seen moves from the original paraffin vapor burner through very large large wattage electric lamps, and then to high pressure mercury vapor lamps, following through onto low wattage, high efficiency metal halide and low wattage tungsten halogen lamps. With the advent of smaller, more powerful light sources, which have been employed over the last 20 years or so, the efficient use of the catadioptric and dioptric components of the lenses has reduced enormously. However, the ranges produced by these lenses are still kept pace with navigational requirements by the rise in illuminance. For instance, the luminance of the original paraffin vapor burner was 30 to 40,000 candela per square metre. This rose to 4 million for the large filament lamps such as the BSL-7, the 3.5 kilowatt unit, and 2.6 for the 1,000 watt metal halide lamp with an etched arc tube. This progression in source luminance continued through to an amazing 12.5 million candela per square metre for the small tungsten halogen lamps. Employed at the same time as the tungsten halogen lamps were the smaller metal halide lamps, down to 35 watts in power, but still offering as much as 6 million candelas per metre. LED light sources are being continuously developed and can currently produce 5 million candela per square metre. Who knows what it will be next week? This picture is just to illustrate the physical size of the old BSL-27 lamp, which was a 3.5 kilowatt 100 volt device. As you can see, there are good reasons to use LEDs as source luminance for ATON lights. All these advantages lead us to consider LEDs in many instances. They're now widely used in aids to navigation, and their progression to replace the light source in traditional optics is an obvious one to explore. Significant savings in electricity costs, manpower, and replacement costs all lead to the consideration of their use. Later in the presentation, I'll show you an outline business case that I hope illustrates the point. There are, however, a few disadvantages to overcome. I'm sure we can get there. The approach to reuse an existing lighthouse lens accords with recommendation number 8 from the Santander seminar. So we'll consider establishing an LED light source in a historical optic. Developments in LEDs have led to the possibility of using a flat LED, rather like this one. As you can imagine, I had quite some problem getting this through customs, as it looks like something else. This is a 13-watt flat LED, citizen LED array. As you can see from the polar plot, for an arrangement of 3, 4 or even 6 LEDs, then an acceptable distribution of light can be achieved. Problems that need to be overcome, I showed you on the disadvantages slide. They are that the light spectral distribution of white LEDs has a little red content, which means that they may not be appropriate if the light in question has red sectors. The light output reduces over lifetime and is dependent upon the operating temperature. Therefore, the decay of light output must be known and a planned replacement period defined, and of course the operating temperature controlled. Also, LEDs come in a limited number of package sizes and light source shapes, so the engineering may take a little ingenuity. I'm sure we're not short of that. So for use in rotated lenses, they may be the perfect solution to low power and reliability. And they're also ideal for using fixed lenses, as coding them is straightforward and there's no filament warm-up time or digressing requirements. This shows how the flat LED can be utilised to offer replacement light source for historic optics. In this trial, the maximum operating temperature specified by the manufacturers is 87 degrees centigrade. With this mounting arrangement, the temperature rose to 80 degrees centigrade when it was run on a 50% or isophase character in an ambient temperature of 20 degrees. This illustrates a solution for heat management. When a larger top piece was fitted, the heat management improved markedly, and a steady temperature of 68 degrees was reached for a continuous LED operation at the maximum power of 4 by 13 watts, 52 watts in total. When this arrangement was mounted in a third order catadioptric fixed beehive lens, it offered a range of 16 miles. That's an intensity of 17,000 candela for 52 watts during the flash. That means that we can achieve a 16-mile range for, say, 5.2 watts at 10% character. Different example now. This shows the employment of a modern design sector light, which is to be installed at Start Point Lighthouse in England. The picture illustrates the existing subsidiary light, which offers a fixed red light with a range of 12 miles. A new navigational requirement was determined for 9 miles, so an LED solution became obvious for consideration.